morning. First of all, welcome to the second day of the workshop on nonlinear and hybrid system control. And it's my pleasure to introduce Professor John Ligeiros from ETH of Zurich. Professor Ligeiros is well known for his many contributions in control systems, in particular sensor networks, hybrid systems, especially stochastic hybrid systems, but also in many application areas like control of energy systems and urban traffic control. The title of his presentation is Data-Driven Control of Urban Traffic Systems. Please, Professor Ligeiros.
Morning to everyone. Thank you very much for the introduction, and thank you to Elena and the organizers for the kind invitation to join this lovely workshop in honor of Marika. I'm John Ligeiros. I'm from ETH Zurich, the Automatic Control Lab, and I'll give you today. I'll talk about a topic I don't often talk about. Actually, it's the first time I talk about this because we haven't even written the paper yet, and it's not really hybrid, not really networked, but touches upon these things, just sweeping them under the rug by using data, basically. So if I get the mouse here, get the pointer. Before I get started on this, I was trying to remember back when I met Marika for the first time. And the first time I don't remember exactly the year, but it was just when I started grad school in Berkeley. It was, I think, a first-year student, so 91, 92. Okay. Anyway, and Marika came to give a seminar in Berkeley at the time, and she talked about her work with Jesse that we heard about yesterday. I must admit, I don't think I understood very much from that seminar, but in my defense, I was like a first-year student, so I didn't know very much at the time. But I was very impressed by the depth and rigor of the work that she was describing, so I decided to try my hand at nonlinear control as well. Then, after trying for a couple of years, I realized I was sort of not as smart as some of the people who heard yesterday, so it was for smarter people than me, and then moved on to hybrid systems. And there I found Marika again, and that's when we started collaborating a bit. This was when I moved to Europe, and I lucked out because just when I was moving to Europe, hybrid system was becoming a thing. So we had a series of research projects jointly. The first one with this very ugly logo when I was in Cambridge, the hybrids project. This was stochastic hybrid systems in air traffic, and I believe that's where your work with Elena started on the observers for hybrid systems. And then moved on. When I moved on to Patra, we had a couple more projects there, the HiCon Network of Excellence and the iFly, which was the continuation of hybrids with Maria Prandini. At that time was Brescia, then Milano, and a number of people, Eurocontrol and NLR around Europe. And that even continued later with HiCon 2 after I moved to ETH. This was all done to a large extent through exchanges, and Giordano, for example, came to visit my group. Before him, Luca we'll hear a bit earlier in the Berkeley days, maybe a bit later. So it's been going on over the years, and I'm still impressed by how Marika has been handling the research field and contributing throughout all of these years that I've known her work. Okay, now to the topic of my talk. I'll talk about sort of network control systems, but not quite. I'll talk about network control systems for lazy people who don't understand networks very well. So basically, there's sort of three steps to this. I'll start with a very network system, which is urban traffic. I'll show the results we have for our case study, which is in the city of Zurich. We're talking about several thousand streets, intersections, hundreds of thousands of cars, and so on, all of them linked together. So it's a very network and very hybrid. You'll see some typical sort of plots later. But basically what I'll do is, instead of looking at all of this very complex, this complexity, I'll just use data. It's a very machine learning type thing. It will not be machine learning. I'll just use data, but not in a reinforcement learning sense or you know, what you would expect from machine learning, using system theory interpretation. So I'll use data to control the system, and then basically based on this, I'll try to formulate control problem, solve a control problem, and show how it works. Now, when you do this with data, the problem is things like distribution shifts and other problems you find in machine learning start arising. So you cannot really test on the data you use to train the system. And for this, I'm going to use, also mentioned yesterday by a couple of speakers, what we call digital twin. So basically, we'll build a simulation of the whole of the city of Zurich and test our algorithms on it, just to see what the effect of the algorithm is. So if the data shifts because of our actions, there's a distribution shift, then we will sort of not worry about it because we are simulating the real thing anyway. And that's the project that we called UnJam for removing traffic jam. It's with a number of people, coincidentally all of them Italian, as far as I know, none of them from L'Aquila. Alessio Rimoldi is a new doctoral student. He started last year with me. I was also his master's thesis that I'll talk about. And then Alberto Padoan and Carlo Cenedese, both of them are professors now, one in UBC and the other one at Delft. We have one paper on the topic last year at ECC. It's a very preliminary. It doesn't have the results on the city of Zurich that I'll present. Some of these people may be familiar to you. Alberto, you may have heard from the In Control podcast. He's the host of the In Control podcast. If you don't know what the In Control podcast is, you're missing out. Go, check it out on I don't know, Spotify or Apple Podcasts or wherever you get your podcast from. It's a lot of fun. Many famous people interviewed, some in the audience from control theory, also historical perspectives, and so on and so forth. Speaking of In Control, a word from the sponsors, the National Center of Competence in Research, Dependable Ubiquitous Automation, because that's very difficult to say, we just say NCCR Automation. That's our national center. I have the privilege of being the director of that, co-directed with Gabi Hug. And it's a center that brings together all the control engineers in Switzerland. You may see some familiar faces here, Emilio and Florian, Melanie, and so on, as well as friends from other areas like Andreas Krause in machine learning, operations research, Daniel Kuhn, and then people from application areas like Gabi, my co-director, who's in energy, or Nicolas Geroliminis in mobility, and I will be sort of mentioning some of his work later on this. So it's a very big center. You see the number of people involved in this, and it caters to research, which is what we do, and I'll talk about, but also other things, including education, outreach to schools, technology transfer, and in addition, the In Control podcast, the sponsor of the In Control podcast. Have a QR code here if you want to follow us on social media, and if you haven't checked out the In Control podcast, like I said, it's pretty cool too. Okay, now to the topic of traffic. I probably don't need to convince people that this is quite important. 15% of global CO2 emissions due to surface traffic, vast investments to alleviate it, and in Switzerland, commuters waste like 54 hours a year stuck in traffic jams. So we try to do something about this. The difficult bit here is that it's a very big system, very large scale, very networked, and a very complex nonlinear dynamics. So doing model-based things is not easy. People have tried that. That's Nicolas Geroliminis and Isik Sirmatel wrote a series of papers on using model-based controllers and PC-like controllers for this. It's tricky because fitting the models is not easy. And you need a lot of transportation knowledge to understand exactly how this works. On the other extreme is complete data-driven machine learning approach. The difficulty there, people have tried that as well. The difficulty there is that if you're trying to train neural networks, you need a lot of data, and then you suffer from distribution shifts and things like this. And it's very difficult to interpret what they're doing. So people have tried this, but they don't scale very well and they're very difficult to train. We tried our hand at this a while back on highway traffic, and then we realized that you need several tens of years, decades of data, if you were to collect real data, to train even passable controller, not a very good one. So we're trying to strike a balance between the two. So one point to get that balance will be data-driven representation of the traffic dynamics. And the second will be the digital twin. So we'll use high-fidelity simulations of the city of Zurich, run on this platform called Sumo. It's an open-source software for micro-simulating traffic. And then we will have an interface, this is what we call ANJAM, an interface in Python, down to the algorithm that we'll use, and this will be what we call the deep C algorithm, the data-enabled predictive control, using data to make decisions, then feeding this back to the system. So we'll close the loop like this, and we'll treat the simulation as a real-world model. So that's our digital twin. So that's what I plan to talk about today. I'll first of all discuss the data-driven representation, which is using system theory interpretation to get a data-driven representation of the dynamics. Then I'll talk about the closed-loop control problem and give two examples using dynamic traffic lights and a dynamic speed limit if I have time. I also have a few slides on the actuator selection, but I commented them out because I don't think I'll have time to talk about this, but you can use similar tricks to decide where to actuate in your system. So let's get started on the data-driven stuff. I'll model a traffic network. This is the streets of the city of Zurich. If you've been there, you may see there's a big hole here. It's a lake, so there's nothing there. And then there's the downtown over here at the side of the river. And then there's the different regions around it, which are sparse and more residential. So my data will be the demand for the traffic. This will be an external input, and this we estimated from loop detectors that give you actual traffic demand for the city of Zurich. This is origin-destination pairs and vehicles per minute between them. Changes as a function of time, of course. The density, which is how many vehicles per meter, kilometer you have, and the flow, which is how many vehicles pass over per minute. This you can also collect information that you can also collect using loop detectors. So this is magnetic sensors buried in the roads. There's lots of those in Zurich. Now, because there's tens of thousands of roads, we won't be able to do control at the level of individual roads. There's thousands of intersections. Hundreds of them have traffic lights. So we won't be able to control each one individually. So we group the city in chunks, regions. These are highlighted. There's 7 of them. We do 7 of them. These are highlighted here in different colors. This is a fairly standard trick done in transportation studies to group cities together. And then you get the graph. That's all the cities and how they connect to them. The one in the middle is the center of Zurich. And then you have, for example, origin-destination pairs, traffic that goes from region I to region J, and traffic that's generated in region J and stays there. And the traffic going from I to J can follow any of a number of routes to get there. Now, we measure, like I said, density and flow, and because we have lots of measurements all over, city is instrumented very well in terms of this. We'll just aggregate these measurements into the regions. And then in each of the regions, there will be a few actuators that we will be able to actuate. These are selected traffic lights in some cases, or variable speed limits that can change the speed limit on a chunk of the road at will. Now, underlying this, if you're a transportation engineer, is a very complex, nonlinear, even hybrid model. I just have one generic equation because I will not use it at all. Basically, the density at the next time instant is a function of the density at the current time instant, the control inputs that you apply, how you control the traffic lights, and so on, and the demand that you get. And then, like I said, we're aggregating the density. We have many measurements in one region. We take their average, and that's our output. Right? So we'll have 7 outputs, 1 for each region. Okay. So the function itself is not exactly known. Transportation engineers fit curves to these nonlinear functions so that you can get some understanding of how they work and there's reasons why they look this way. But in general, we don't know this. The averaging function we do know is relatively easy, so we can just average our density. It's our measurement equation. Right? So what we will do, instead of looking at this, we just look at the input-output behavior of the system. That's in the Jan Willem's sense, the behavioral approach. So we look at the outputs, which are the densities, the average densities, and we look at the inputs, which are what we control, and the demands. And then we just write sequences of these, of inputs and outputs as a function of time, and use these to characterize the system. So you can think of the set of sequences of measurements, inputs, and outputs that satisfy this equation. Right? Without knowing the equation, you can still define a subset of the sequences and call that your model. And that's basically the behavioral approach. We'll use U for these two, the controllable and uncontrollable input, and Y for the output. And then we'll just use the behaviors as a subset, the image basically of a map that we generate using data. So that's paper by Florian, my colleague, and Ivan Markovsky that describes how to do this. It goes back to work by Willems good 20 years ago. Basically, this data matrix will be a Hankel matrix that you construct using historical data, and the range space of that matrix will be what gives us the behavior. This system is nonlinear, so you shouldn't expect the range of a Hankel matrix to give you anything, everything. But we will treat this as a local linear approximation of the dynamics. So it's in a sense it will be a piecewise linear approximation of the dynamics based on what you've seen in the past. You sort of use chunks of the Hankel matrix to extrapolate the future, but we let an optimization algorithm do this chunking, so they will not manually pick columns of the Hankel matrix, we just let the optimization algorithm pick those. Okay. So how do you do control? How do you do control with this representation that involves basically a big matrix constructed from data? Okay. So you formulate an optimization problem. This is an optimization problem that looks very much like MPC. You have a prediction horizon, you have a cost, and you have a number of constraints. I'll just walk through one by one just to explain what they are. I'll start with the cost function. So I'll be doing reference tracking. I'm trying to minimize congestion, so I'm trying to maximize throughput from the highway, from the system. On the plot here, you see experimental data from what you call a macroscopic fundamental diagram. This is simulated data, it's not really experimental. This is the macroscopic fundamental diagram, is the relation between the density and the flow. Where you want to be is maximum flow, so push as many cars as possible through that part of the city. The little dots are simulations times, and you see this characteristic sort of upside-down bell curve. That's why many people model it as hybrid. There's a section here which is uncongested traffic, and a section here which is congested traffic, and then basically two distinct regions of before congestion and after congestion. So where we want to be is near a density that ensures the maximum flow. So we'll use this as a reference for the output, for the density. Then we have a reference for the input that's actuator dependent. Usually traffic lights, for example, have a fixed duty cycle in them. So we'll try to stay as close, because this is hand-tuned by transportation engineers, we'll try to stay as close as possible to that. Same thing for speed limits. There's a generic speed limit in the city. We'll try to stay close to that. Depends on what actuator you use. Then there's a term that has to do with regularization. This is needed because if you start fitting things, then you need to sort of make sure you don't overfit. And that cryptic term here ensures this happens. I will not go through the details, but basically, I'll just say a bit more when I describe the main constraint, which is the Hankel matrix. Then you get, as in MPC, input and output constraints. Duty cycles of traffic lights are between 0 and 1. You cannot do anything more. Speed limits are bounded. You can have your output, for example, the density. You want to ensure that there's no negative, so you can add a constraint about this. There's the jump density I had in the previous slide. This is the density here where everything collapses and the street is full of cars, basically. So you can limit the upper bound as well. And then finally, the more important constraint, which is this Hankel matrix constraint. This is a Hankel matrix constructed with historical data, and you use this as an implicit predictor. In MPC, you would find a model there. We don't have a model, so we put this Hankel matrix as a constraint. This is the data. This is the decision variable G. We try to match the past data we measured from the system up to now for a few seconds in the past, and forecast a few seconds into the future, a few minutes, I would say, into the future. Now, because the system is nonlinear, you cannot expect the behavior of the system that you measure to actually lie in the range space of the Hankel matrix. So we relax a little bit, allow some slack, and then we penalize this slack to make sure that we match the Hankel matrix as much as possible. And then to this, we add another regularization term, which is basically trying to make the G vector sparse, meaning pick few columns as possible. And that sort of has this intuition of you adaptively linearize the system by picking a subset of the columns. You don't hand tune this, you don't pick them one by one, but you let this regularizer, so usually one norm regularizer, pick it for you. So that's the problem formulation. That's, we called it Deep C in this paper in ECC 2019 with Jeremy Coulson and Florian. And this is the algorithm we're going to use to control the traffic. Okay, now to specifics, to some results. We tried two types of formulations for control. This is again the same stuff I had before. This is my region, the region J. This is where I measure. I take the average of all of these to get the average density. This is what I actuate, traffic lights. How do you actuate traffic lights? They have a duty cycle, and we just play around with the duty cycle, the fraction of green time, which is naturally bounded between 0 and 1. In principle, you could actuate the phases, but that would give you a mixed integer program, and we don't want that because it's a lot of work to solve, and it breaks the hypothesis, the linearity sort of approximation that we do with the Hankel matrix. So we just actuate fractions of time. So basically, we turn these duty cycles of red and green into a number between 0 and 1 that we control. And this will change every 90 seconds or so, which is the duty cycle of the traffic lights. Okay. The second input is variable speed. Also, some of the streets can be controlled. Controlled streets means that the speed limit, you may have seen it on highways, it's very common. In arterials, it's less so. There's a speed limit that changes over time. So you drive one day and it says 50, and the next day it says 40. Okay? Now, clearly, you cannot change this continuously either, another continuous nor all the time. So if you, again, have a binary variable there, it's going to make your life difficult. So what we do for that one is, again, we approximate basically by pulse width modulation. So if you take a chunk of time, and then you separate, for example, 70 to 50, and that gives you a number between 70 and 50, and you can treat this as a continuous quantity and control using that. Okay, so how does it work? So what we did is we tried this on a case study of the city of Zurich. We partnered with a company called Transcality that has built a very detailed map of the city of Zurich that you can import into the simulation platform that we use and run the simulation. It's very realistic. It contains, you see here, almost 15,000 roads, almost 7,000 intersections, 800 traffic lights, and then any number of different vehicles cars, vans, and trucks, and buses, and so on. If you've been in Zurich, you may have gone through Bellevue. Bellevue is one of the most complex intersections that we have in the city. It's by the lake, so this is where the lake on this side meets the river on that side, or rather the river flows out of the lake, to be more precise. And this is like trams going around and all sorts of cars and so on. So this is a little bit chunk of simulation. This is a micro simulation, simulates individual vehicles with following policies and so on. And you see them in the different traffic lights around this intersection that we can use to control the flow of cars. For the actuators, we went to the city of Zurich. The city of Zurich has 47 traffic lights around the city that they control. They now control them mostly, whose duty cycle they control it mostly manually. They've positioned these on purpose on high volume traffic flows. And what they're trying to do with these is try to protect the city center from congestion so that you get as much flow through that as possible. The flip side of this is they tend to hold people outside the city center for a long time. I have one of these, it's a drive from, I used to come into the city, and you see that there's cars backing up there because they're just trying to keep them out there. So what we'll do is we'll actuate these 47 traffic lights that the city of Zurich actuates anyway, but instead of having fixed rules and manually changing between them, we'll just do it automatically using this deep C algorithm, the optimization algorithm. Two case studies. This is traffic in the city. One will be the congested case. You see the red means congestion. And on the right is a lighter traffic. These are two rush hours, two different rush hours. We use data from real loop detectors to generate origin destination pairs, and we instantiate the simulation using that, and we just increase the level of at which the cars come in with the same origin destination pairs to congest or uncongest the city. And this is how it works. This is the uncongested case, first of all. This is the no control case. This is whatever policy is fixed to the traffic lights to start with. The last one is our approach, this deep sea approach, using the data to do this. And then in between is the method I mentioned earlier from Nicolas Geroliminis and Isik Sermatel, fitting a model, a linear model admittedly, and then trying to do MPC with this. And this is how it works. You see, you do get an improvement with MPC over the travel time and the waiting times and the CO2 emissions, but of course you get much bigger with our method. This is the total savings that you get in terms of hours spent during the uncongested case and CO2 emissions. And you see it's quite substantial, 13% savings in terms of timing over the non-control case and 8% savings in CO2 emissions. That's for the uncongested case. For the congested case, it's not as good the percentages because the city is already at its limit, so it's trying to carry as much traffic as possible. So basically, you're going to delay people no matter what, either in the city or outside. So basically, the algorithm does what they do manually now, trying to keep people a bit further out so they don't congest the center of the city. You see the savings are a little bit less, are quite a bit less. It's 3% and more or less for CO2 and hours. But of course, the numbers are bigger, the absolute numbers are bigger simply because there's just so many more cars in there. So you save quite a bit in terms of tons of CO2, even though percentage-wise it's not that much better than the uncongested case. The no control case. Now, why does this work? That's a good question. The short answer is I wish I knew. There are some reasons why you would not expect it to work, because it's very much a linear thinking. You look at range spaces or the images of matrices in a nonlinear system. So a linearly inspired control on nonlinear dynamics. Our conjecture is that the reason why it works is this local linearization type by sparse column selection. So this is something we also observed for the first time when we tried this method on energy management in buildings. And there you saw very clearly that the system was just picking a subset of the columns that had to do with the ambient temperature to do the control. So it sort of figured out, it was a mildly nonlinear system, so it figured out by itself which columns to pick to just do the control. And this in turn suggests that the input-output relation we're looking at from flow, from density from the traffic lights to the density is actually more linear than it seems. So it looks like it must be a very horrible relationship there, but it's probably not too nonlinear. And we're trying to figure out a way of sort of quantifying this observation. This is further supported by the fact that when we try to do the same thing using flow, it actually made things worse. Even when we added the density, to the density we added the flow, it didn't work quite as well. And we think the reason for this is that this mapping from flow, from the traffic lights to the flow, or from flow to the density, is a very nonlinear one. Just to remind you, this is what the macroscopic fundamental diagram looks like. And you see from the density, you get a very well-defined flow, but from the flow, you don't get a well-defined density. If you have 150, for example, vehicles per minute, then you could either be uncongested or congested. So your control input should be completely different depending on which leg of this you are at, and you cannot tell from the flow which this is. So you have to go probably for binaries or switch system or something hybrid if you were to capture this. Okay. Another sort of interesting phenomena is that we had two actuators that we considered. I mentioned the traffic lights and the variable speed limits, and they both seem to have the same effect. Basically, you can see the free flow speed here is the slope of the curve. This is vehicles per kilometer. This is vehicles per minute. So the slope is basically kilometers per minute, kilometers per hour speed. That's the free flow speed, how cars would flow through. And by changing the traffic lights, basically this is macroscopic, the effect this has is it maintains more or less the same critical density here, but it changes the slope. It makes it steeper. So you can pump more cars per minute. And change the speed limit has the same effect. And that we see, for example, when we tried this with the speed limit. Now they don't actuate speed limits in Zurich, but we can do it in the simulation. So we hand-picked a bunch of roads, and we actuated, you see them marked here. We actuated the speed limit there using this pulse width modulation scheme. And then you get, again, savings, average time, in average travel time, waiting times, and so on, comparable to the ones we had with the traffic lights. here you see a little bit what the system is doing. This is also trying to delay cars, for example, to the algorithm sort of pulls some of the demand earlier so that you get to avoid congestion later on in another area. So basically this is the center of the city, this is in the periphery, so you keep cars a little bit more in the periphery to avoid congesting the center at a later time. Okay, so that's it. I'm going to wrap up. Like I said, we're trying to write a paper on this. There's not even a paper yet. We're planning to send it to transportation research. And the whole idea was a behavioral representation of traffic. And we went for this because it's quite flexible. It has a few knobs that you can tune, but not too many. Not too many hyperparameters in there. It doesn't require a lot of expertise, so it's very good to talk to practicing people, like the city of Zurich and our partners at Transcality about this. And it sort of allows you to combine different things like traffic lights and variable speed limits and so on and so forth. Where we're stuck is we're trying to understand the traffic engineering interpretation, why this sort of two actuators behave in a similar way, are there benefits of having both, and what these are. And like I said, this is really a network system. You so have a small number of regions, but still it's a network system. So we're trying to do a distributed implementation, breaking it down into sub-regions and doing the same kind of calculation, but in a distributed way. We've actually, the theory for this is done. We're presenting a paper at ECC with another student of mine and Alberto in a couple of weeks, how to do distributed implementation of DeepC, this data-enabled predictive control algorithm. And we're going to try it again. We're going to try to the traffic system to see what are the benefits. It's basically, as you can imagine, ADMM meets DeepC. The other thing we're doing is actuator selection. It turns out there is also a data-driven interpretation of gramians. So you can actually write gramians implicitly using data. And then if you have gramians, you can try to do submodular optimization to get best actuator positioning. So for example, if you only have money to actuate 10 traffic lights, which would these 10 traffic lights be? And that we're trying to do with Alessio, who started his doctorate. The second theme was the use of digital twins and this UnJam software that we're developing to interface the two. I think this is very good. It's been very well received by the transportation researchers we talked to, because it is a shortfall in the literature. People develop algorithms and they test them on small benchmarks or different things, and we're trying to develop a full-blown benchmark for Zurich and other cities so that people can try their algorithms there. I think it's also a good fit for the, AI gym type work, but not for robots and things that are sort of not entirely related to the real world, but more for traffic. Okay. And with this, I'd like to thank you all for your attention, and thanks first and foremost to Marika for her contribution all these years.
Okay, thank you, Professor Ligueros. Any questions from the audience? Okay.
So Gilberto Burgio from Collins Aerospace, very interesting work. And indeed, we know about the complexity of using data to train deep neural networks, and this approach is kind of easier to think that it's not too complex to understand, right? Because then a deep neural net for the industry needs to be understood, right? Otherwise, it's not safe, or industry doesn't trust, right? So, so the two questions. So the first one, the digital twin indeed is the database model that you use to implement then the controller, right? Mm-hmm. And then the second is, what about the computational effort that is needed for the application you presented? Yeah. Thank you.
Yeah, so for the digital twin indeed is what we use to implement the controller in closed loop, right? So it's like a two-step data-driven approach. One is we get data from the city, and that we use to instantiate the digital twin. And you could use the same data to put in the algorithm and run the algorithms. That's not a showstopper. The problem with, but you can also use the simulator to generate data, to instantiate the algorithm with the data from the simulator. So you can use for both purposes. We just use the data from the simulator, but you could also use real data. It's not a lot of data that's needed to form this matrix, right? Because that's related to the second question, how difficult the computation is, and this has to do with how far you predict into the future, how much do you need to look into the past, what's your sampling time, and so on, because all of this grows with the number of data, the data points you need, and the computation grows with this. This was not, even for the city of Zurich, we had like 47 actuators, we had the 7 regions, so 7 outputs, so it was like 47 input, 7 output system. So it was in the 50-ish for each time step. And we used 4 or 5 time steps into the future and 4 or 5 time steps into the past. So it was a big but not gigantic matrix. And this you could solve on a laptop. This was no problem at all. Now, if you want to scale up and you want to extend your prediction horizon for whatever reason, it gets more and more difficult, like MPC does, right? And just on your point on interpretability, I think that's the very nice feature with this. It looks very much like MPC. So the only leap of faith is I don't need to have an explicit model in there, I just the implicit model. But I can put the same cost functions and the same constraints on everything so that I can easily understand why it's doing what it's doing, right? So there's very little magic if you believe MPC, and I think most people are very comfortable with MPC by now.
Okay, there are other questions.
Thank you for a nice talk. The fundamental diagram, can you clarify a little bit, was that for certain streets or for a region or all over Zurich? And I suppose that will change over time, so how do you take that into account?
So, correct. So this is a macroscopic fundamental, what they call macroscopic fundamental diagram. It's Nicolas Geroliminis' claim to fame. This is for the whole region. So basically, you take all the data from all of the region, and you plot it like you would plot a normal fundamental diagram for a street, and you get the type of curve that I showed. It's somewhat surprising that at the macroscopic level you also get the same type behavior. This will change over time, but we only need one. We don't use it at all, right? It's not baked into the model. It's only the data that we use. So you can just take new data and put it in there. The only thing we need from the macroscopic fundamental diagram is the critical density, which is we use in the cost, right? And that's because normally we would use the flow, but it becomes very horribly nonlinear, and it doesn't work all that well. So we use the critical density. So the only thing you need to extract is that, right? So if it changes, you just need to, if you do construction, you need to figure out what the critical density is. The difficulty with this is that the distribution shifts, right? So once you start doing control, the fundamental diagram changes because you change in the traffic light, so more traffic comes through, so it looks different, right? That's why we plotted it before and after, and to our pleasant surprise, the critical density did not move very much. It seems to be something that's in the, like the jump density, a function of the topology and not of the control you use on it, right? Which makes life easy because if there was a distribution shift, we'd need to try, take new data, do it again and again and again to convergence. But it turns out that you affect the free flow density, not the critical, the free flow speed, not the critical density. So we lucked out there.
Okay, thank you. If there are no more questions, I have a comment because I was just thinking that you have 2 actuators, right? Traffic lights and speed limits. Well, it depends on the country, on the town, how drivers respond. Because you dealt with the Zurich traffic in Switzerland, but I was thinking in Naples or in Rome, how a driver, when we see yellow light, we accelerate. We don't slow down. So it's a opposite behavior. Right?
Yeah. You don't need to tell me I'm Greek, right? So,
okay, But since this is So it is difficult to model the driver in different cities, but this is data-driven, so if you acquire data from Naples, you get different studies. Okay.
I won't stick my neck out on that one, but yeah, in principle.
Okay, thank you again.
Okay, thanks a lot.
Okay, it's my pleasure, my honor to introduce the next speaker. This is Professor Shankar Sastry from University of California at Berkeley. He's well known for his main contributions in control systems, especially in robotics, autonomous systems, sensor networks, and adaptive control, of course, and many other fields. And unfortunately, he's not here today, so he will give his talk remotely. And the title of his presentation is Embodied Intelligence from Cyber-Physical Systems to Neurosymbolic Reasoning. Professor Sastry is online.
First of all, say, it's really a pleasure to talk. I was thinking back about when I met Monica. There was a conference in Berkeley in 1989 called Nonlinear Flight Control, which George Meyer and NASA Ames and I had organized. And actually, August 19. My memory was jogged because of last month or so I was at Brown. Frank Doyle was a graduate student who brought out a copy of his poster, which of course had Monica's name, speaker. And so I think that must have been the first time. And I continued to work with her and so in 1990, 91, I spent part of my sabbatical at the University of Rome working on adaptive and nonlinear control. And over the years, it's really been a privilege to work with her on all of these topics. And she said, be sure to be entertaining. So I tried to keep the equations down and really to talk a little bit about coming a full circle from adaptive and nonlinear control, which are all in there, and hybrid systems, it's all in there. And I've just started a new laboratory here called Embodied Intelligence and Robotics. There's no I in Ember, but it's there. So let me give you an idea of what this is up to. And so let me start this slideshow mode. Can everybody see the presentation? If somebody could do a thumbs up from the audience, that would be okay. I presume it is. Okay, so last year's economics Nobel laureate Domenica gave a talk where he quoted these developing graphs from Goldman Sachs and McKinsey, the graph on the left, and Goldman Sachs, and it paints a view of how general intelligence, artificial general intelligence, AGI, is going to grow the market at some ungodly rate, and the wages are going to drop in the next 20 years. And then McKinsey has a report about how McKinsey says 6%, and Goldman Sachs that generative AI could raise global GDP by 7%. And of course, the newspapers are full of this on a daily basis. But what Daron said in the talk that I invited him to give in 2025, based on some work that he did for the National Bureau of Economics Research, is that in fact, and I won't read all his text, but his estimate is really that only 20%, actually 19.9% of the economy is actually exposed to AI. And of that, only about a quarter, 23%, is profitable to operate. And in fact, without having intelligence in the embodied world, what we call embedded systems and cyber-physical systems, which is the red bar on the left, his own estimate of the increase in productivity growth is only one of GDP is only 1.4%. Of course, now with current economic forecast, maybe that's even become negative. But the short answer is without embodied intelligence in the physical world, and bringing AI to the physical world, the premise of this growth is unlikely to be met. So let me just tell you what the challenges are. And let me go back to really a little bit of where we come from when we think about. Let me try to lead you through this little picture on the left. These usually come up in anatomy books and neuroscience books. They're called homunculi. And this is area 6, the motor cortex. And that funny map, homunculus, that's what homunculus means. I don't have to tell you that an audience what the Latin word means. But homunculus is a map of the body onto that motor cortex. It's left motor cortex, right motor cortex. And so it's half the body. And it's from looking at it, it's really amazing to see that really more than 40% of the human homunculus is used to control the head. And a very small fraction is used to control the legs and the bigger parts of the body. Another 40% that way is used in the face and the facial muscles, chewing, and all of those kinds of things. And so you can see that. And so, not surprisingly, one of the earliest philosophers, Anaxagoras, who we consider the patron saint of robotics, said that somewhat controversial statement that the mind exists to control the body, because Socrates began with him, but then pushed it way aside, would argue about whether Anaxagoras had it right. But nonetheless, it points to the need to think about embodied intelligence. And so that brings us to what is the successor to hybrid systems? Nonlinear control, adaptive control. And that's been sort of my journey, adaptive control, nonlinear control in living systems. And I think that the successor to this is what we are calling neurosymbolic reasoning. So let me lead you through what this means. The short version is that, in the famous Gartner conference in the 1960s with John McCarthy, who's credited for having made up the word AI, came up with formal logical methods of reasoning and symbolic reasoning. But then he was a student of Wiener like others, but there were other students of Wiener, McCulloch, Pitts, and others, who came up with neural network models. And then I think we've gone through these waves of symbolic reasoning, and that nonlinear control as a whole, even information theory to some extent follows from that. We said formal methods, and so several talks yesterday on formal methods. So that is the symbolic reasoning. And the neural part is about strengthening synapses. And of course, deep neural networks, foundation models, LLMs, VLMs are changing the world. However, the problem is that for safety critical systems, and the gentleman from Collins made this point at the end of John's talk, is for safety critical systems, it's impossible to do away with hallucinations and DNAs, deep neural networks, foundation models, large language models, which models VLMs, and to come up with certificates that so can allow them to be insured and interpret and bring them into the physical world. Another piece of this is that a number of solutions that you see coming from OpenAI, Googles, Amazons, and so on and so forth, are very important. There's a lack of robustness in this real-world integration. Everything works great in simulations, but it simply does not work in reality. And this is being alluded to as the Central Reality. Put up some names of simulators. I think it's the NVIDIA simulator, Joko, PyGen, etc., etc. So think that this methodology of neurosymbolic reasoning, the set of design tools we span symbolic methods, which include our heritage non-linear control and neural network methods, provide all the benefits of crossing the chasm between central bits. So let me have show you 3 vignettes. This is a bit of a fun talk. I'll try to stay within my limit. The very first one is about neurosymbolic control, and we know this is the phrase that's now making its rounds, GC for geometric control and RL. And the tension of RL is really a version blocking control with rollouts and adaptation to domain randomization. And this is, I want to show you what this looks like for a quad rotor. It's a little more than a quad rotor. It's maneuverable. It's hyper-maneuverable in the limbs, and also the four limbs can also be changed. Okay, so I'm sure you heard about flatness. You know, this 6-12-state model with some additional dynamics with motors, but perhaps about 20-dimensional model. They really are pretty close to flat, and the problem, of course, is that you build these flat models or dimensional models, linearization, and some dynamic extension to get them, the version that I showed you had 8 inputs and 4 inputs, control 4 outputs, the XYZ position of the rotorcraft and the yaw. If you have 8 inputs, there's more inputs, 6 outputs, control 6 outputs. And so you build these forward models, and because the parameters of these linearization are unknown, you use neural networks as function approximators to be able to build forward inputs models as neural networks. They're not usually particularly deep, but the depth now comes from adding on, it's not symbolic model control, then you need to do something called domain randomization, as well as trying to get the parameters for different kinds of wind, payload, etc., etc. And, it's optimal control means nonlinear control. Nonlinear control doesn't do as much with Hamilton Jacobians and rollouts, finding out the new parameters, having stochastic gradient directions. And by the way, it's rewarded for optimal control. It's quite not trivial. I haven't met any one of these problems that likes linear quadratic cost functions. For example, for this quad rotor, some of the best cost functions need to be exponential, in that they discount large errors rather than negative exponential, so you discount large errors. And so when you put all these together, it is as though you use the symbolic methods for the feedback linearization, and you use optimal control, optimal control of learning, which is RL, reinforcement learning, for the domain randomization. And the training trajectories are the ones that provide a certain level of robustness. And depending on the richness of the trajectory, this example of what these trajectories might look like, you can use, they have to be rich enough in the way that we've talked about in adaptive control, provided they're rich enough, they can come up with trajectories that are pretty good. And then the questions of assurance, these performance boundaries. And let me get to that assurance in the end, just to give you a sense. There are lots of things you cannot model, the ground effects. If this thing was driving through a complicated environment, there's all kinds of things that we have to deal with. And the advantage of the RL, so here, the red trajectory is the vision system is trying to, the blue trajectory is the desired trajectory being generated by the vision system using one of these neural methods called diffusion models. And this is just to show you the complexity. these models of these flying under the canopy, that's flying through trees, the urban environments. And you can see that even with gusting ground effects, which do get modelled here, and it's flying upside down as well, it produces really quite excellent trajectories here. And also, just to give you a sense of acrobatic maneuvers, it's not like a unicycle, it's not a plane, it's a full-scale models which involve, exercising a certain degree of freedom. And here is an example of a listen-to figure, in a full 3 dimensions, which sort of does this loop in there in order to either demonstrate what we call this listen-to figure to figure 8 in order to be able to exercise all these degrees of freedom with the tilt rotor. These tilt rotors are now being quite popular, in that they're being used inside air taxis, all of this personal aviation. So here's an example. But then I thought, again, for an Italian audience, I wanted to show you sort of all this in effect for, I recently had an occasion to buy a robotic race car. And I want to lead you through the control of this robotic race car. And, it's a little bit about this. There's a Formula One league, and there's something called Indy cars. These are Indy cars, they're like Formula One cars. Everybody has the same hardware. All the cars are made by a company in Modena called dell'Aquila. So you can see that in the lower left. This is a Cal team, AI racing tech. And so, they've been racing this car using neurosymbotic methods. So I want to give you a sense of what this is. This is not like...
Grade has been given and is next to target speed threshold of 125 miles per hour. The trailing car will have 2 laps once again to make that pass. The world's fastest autonomous race cars valued at over $1 million a piece. Completely autonomously duking it out here in Las Vegas by this weekend.
The second lap, it looks like they're going forward right here on the first one, which is great to see. I'll go over on close alert to the guys on
So what you do that?
They said that Robert Lucas had himself was the fastest ever gone. So here they are.
Given 2 laps.
In the territory they've driven, it's great to see.
Once again, it's up to AI racing tech to answer the challenge that the green's been given or not, but that car's awfully anxious. No green yet is the word for race control. So coming around, they'll get it in turns 3 and 4. The next sequence coming up in just a few moments, but I can almost sense this car's perhaps a bit more comfortable with a little more speed.
Yeah, you get a little bit more downforce. The tires get a little bit warmer too, so maybe they are a little bit more comfortable as they go. As they warm up and get a little bit further in, but it also gets the risk a little bit higher too. Looks like there's maybe tank or wrap flapping around underneath that car that should be able to shoot. But yeah, it's the one thing we have to be careful is at higher speeds. You do need to be less aggressive with the steering wheel and the braking. Actually, you're kind of whistle when some of them are backing out in the corners, and as you get the higher speeds, they actually cause you to slow down. So the controllers are definitely sensitive to the speed that they're going.
And so on and so forth. So you can see, the control car, you have to be able to optimize your mind.
So it's the first flying lap for AI racing tech and Pit RW at this level, and an easy pass made on the entrance to the corner. It does need to consolidate the pass by a rule.
Okay, and so just in the interest of time, I won't show you that. Then this is Las Vegas. This is sort of BBC with multi-car racing, which is what I really want to talk to you about. And this is to show that, with all the senses, you've been racing in the darkness, and this is BBC footage of
Just tiny. There is a serious side to this.
Okay, so what's the technology that goes into this? So this is a little bit about the cars themselves. AB24 and the 2024. Everybody has the same hardware. It's GPS. And, passenger PIR, radar, multiple redundancy, and so on and so forth. So they're quite well-equipped cars. Everybody has the same hardware. It's only different software. And there are different teams. That's why we have a big gang there, which does these 6 functions. And autonomous racing has been in Indianapolis where this began. And then in Monza, they were set up by the car companies to mature new technologies. And what I wanted to show you is what's the theory. Certainly there's theory involved in developing MPC width or some reinforcement learning on the 2 maneuvers. Then how do you generate competitive trajectories that overtake and block other racing cars? So the first thing you do is to develop what are called racing lines. And these racing lines, I didn't know all this time about these cars, but if you look at these racetracks, there's only a very small piece of the track that's actually used in order to be able to get it's a game of inches. And then we start coming up with Markov games for these n-person racing teams. And the problem with these multi-agent Markov games is that the strategies do not converge. So-called PPO strategies, which are all popular in AI, don't converge. But we've come up with a way of thinking about them called near potential games. And these near potential games is sort of if you had, so what we're trying to do is build an algorithm, real-time algorithm, which produces a Nash equilibrium, which, it's all continuous time, discrete time, but, it's a dynamic problem, so it's static. And it's a Nash equilibrium with deviation from it. It's bad. And it's an epsilon Nash if the deviation is suboptimal and no more than epsilon. So this is sort of like a prisoner's dilemma kind of Nash equilibrium. And so what we show is that, in fact, for a number of these games, you could come up with what is called a Markov near potential function. And a Markov near potential function is almost like the value functions for each of the agents are close to the gradient of potential function phi. And the question is, how do you compute this phi? And how do you learn phi? And how do you then figure out the strategy of each one of other drivers as you pull this together? So there's a little bit of interesting theory there about Markov games and n-person Markov games, which is going to appear been appearing in the last couple of years, including this year, the transactions, LCSS, and so on and so forth. But these near potential games can be used to come up with a way of figuring out the strategy and really in real time for how you parameterize the strategy with these parameters theta, and these thetas are actually, in fact, the parameters of a deep neural network, and you use some of the computational horsepower of these cars to be able to compute the optimal solutions of these near potential functions, optimal to an epsilon. And so, the question is, how do you learn this? There isn't a lot of data on cars. People say lots of data on the web. Problem with embodied intelligence is a lot of the data is linguistic. It's a little more video data. There's almost no motion. So quite often you have to generate your own data, your own races, in order to put these things together. And so this is where it's called self-play, is the way that you generate the data. And this is an example of these stochastic algorithms you can come up to. You can figure out these things to a large error, but 4,000 races in order to do this. And so, the simplest kind of multi-car racing is 3 cars. And I wanted to show you that with these epsilon Markov games, we're getting ready to try it out this summer. We won't be in Monza, but across the bay from Berkeley, there's a place called Laguna Seca, which will stop the IndyCar circuit in July. We'll be racing multi-car. And so I want to show you sort of what this looks like on the simulations first. And this is 3 cars. The green car is the evil car, the red car is the true opponents. The opponents are running MPC, model-brain control, and this shows you sort of an animation of how these things, a little bit of annotation to tell you. So the blue line is the optimal race. You compute this, and that's what you do in trials. The evil car slows down part of the strategy to get ahead of the model-brain control, and then you can see the model-brain control tends to be a little jumpy, even if it's been forgetting factors. So it's a little too aggressive in some of the turns. And we'll see that on the average, to beat out this model-brain control, this shows you exit paths. So the idea is that unless you're passing somebody, trying to block somebody, then you stay on the outer racing. And, so this it sort of figures this out from the learner that goes into this. And just the way you do this, with other kinds of strategies on control, in which one is the common strategy, the great strategy, is called iterated best response, which means that they see what others are doing, and they try to game theoretically best response to this. And so this is the most common recent strategy, it's a human strategy. The problem with the iterated best response is that you can, as you saw in the result of 2 opponents falling off the track, and so on and so forth. So that's so this is this kind of simulation that goes into doing this. And why is it neurosymbolic? Because it's hard. It's a way of computing. Started with National Library of using learning and neurosymbolic methods to be able to learn the parameters of this value function, which is the partial Markov. So I'm going to end with really trying to pull this all together. What you could be doing. So here is, I've also gotten interested in these humanoids. The humanoids are really, this particular one in the 28 degree of freedom, him being 2 hands, 2 legs. This actually has even 5 20-fingered hands, not until the 28. But, you're interested in trying to figure out how to do this. So even though the Lagrangian equations of motion is 28 times 2, the 56-dimensional vector. For robots, they do something called computed torque. Jesse and others worked on locomotion. Locomotion is bad enough, but here you have, really full 28 degrees of freedom. And what you'd like to do is to take a look at a human being thinking about, doing something like getting out of a chair. And you're interested in the special actions which involve what is called the whole body. It's not just the hands and the legs, but a combination of the hands and the legs. And that's, we've built a system called the verb, which is a whole body vision and language action model without hallucination. So the big problem with all these foundation models is the most inopportune moment, hallucinate. Hallucinate is like a polite word for those nuts. So, you've got to build in these guardrails so as to keep that from happening. I'll talk about that in here, and that's built into it. But we have a vision language model that will actually take a look at human beings, in fact, in simulated actions, and come up with a visual description of what the humanoid is doing, and then use reinforcement learning on this 56-dimensional model to be able to actually visualize this. And again, it is true that you melt the polarized gap in terms of GPUs to be able to train these things, because the stochastic gradient algorithms that go into the training are very, very slow. But nonetheless, I think we can provide this to be an example of how you generate data. And this is this is now synthetic data of the humanoids called G1 sitting in a chair. It's an example of one of the data sets. So we had to generate this data ourselves. Then another example, walk to the round chair, rocky round sofa. Again, go from domestic descriptions to the joint action, the joint angles. And then you convert that into, unfortunately, where we are is that from this learning, what we produce is exclusively proprioceptive data, which is the angles of all the joints, and you try to mimic them. But we all know that it's more than just the joint angles. It's the forces, it's the contacts. By the way, this has got hypersystem, it's got contact models, it's got, in addition to the nonlinear models, it's really, it's got all those features. There's no linear, no quadratic. Yes, you could do linearization on the fly, but I think it's no easier to do linearization than it is to simply use the neural networks in order to put these together. And when you put it all together, here's an example of how you can come up with something that stands out. See, when you stand up or sit down, you actually use your arms in order to be able to stand up. Actually, as I'm getting older and older, I know I really count on my arms to help me get up. So another one is, and this to show you it's because it's only proprioceptive, it can be pretty jerky motion. There are jerky motions there. It's the same. It seems living on the edge of disaster to sit down in a chair. But nonetheless, he is successful in doing this. And finally, this last description is go sit on the blue chair. And you can see he had the sling to make sure it didn't fall out. Okay, so let me sort of, Monica told me, don't make it too serious, so I thought I'd just show you lots of videotapes. But there's a story in there. And the story in there is the intellectual successor to adaptive nonlinear hybrid systems. And that is a conference which we've started, which we had last year in Berkeley called Neuroscience. And the second one was at UPenn last week. As you may know, there's a conference called L4C, which is running this week, now actually, in Ann Arbor. Next year, L4C and Neuroscience reasoning will all along together. And the general story is that, foundation models, visual language action models, are not robust enough. If you want to impact more than this 19.9% of the economy, you have to augment it with safe AI techniques, with proofs of correctness, come out with assurance metrics. And what are the assurance metrics? I think if there were deterministic systems, you could use reality. But mercifully, there is a counterpart of reality. They are the so-called martingale methods. A super martingale is a stochastic Lyapunov function. And amazingly, we can use it. So the story about this, the racing with the absolute Markov game, is that the potential function, the epsilon potential function, is actually a super martingale that actually can be used to provide probabilistic proofs. Having said that, there is some differences between the probabilistic scenarios and the deterministic scenarios. They have to do with the fact that sample function properties are different from ensemble properties. And that quite often is what is the difficulty in the robustness of implementation. In the stochastic literature, we call these large deviation problems. But that real gap is more than just the robustness of the implementation. It's to find out those corner cases where the ensemble properties are okay, but there are specific trajectories which put these together. And just to tell you about the tension, in the formal methods community, there are things like safety properties, liveness properties, reach avoid properties, etc. And those are sample function properties. Super martingales and assurance properties for these are for the ensemble. And so the tension between those ensemble properties, and figuring out, when you train, how to find those corner cases to be able to determine when the ensemble properties actually hold up is actually a wonderful challenge. And, it's a place where even in the face of this incredible amount of data analytics and so on and so forth, there is a wide open area for exploration. And so I want to conclude by telling you that, this agenda of combining adaptation, learning, hybrid nonlinear systems, and really think about AI, the embedded intelligence, is really its infancy. And really is probably one of the most engaging problems in front of us. And let me say that Anaxagoras, I think, had it right. There are other philosophers, perhaps the Heideggers, the others who went off in a different direction. But nonetheless, to me, I think it's a very rich agenda. So I will stop, and I'm sorry to overstate my welcome by Marika, congratulations. I hope you keep going. Retirement, the beginning of a new chapter. So I hope that you continue to enjoy this. It's really too exciting a time to not continue. Thank you very much.
Thank you, Professor Sastry, for your interesting speech. Are there questions from the audience? So it seems no questions. Okay, I just have a curiosity about the strategies for in racing cars. When a policy, a strategy is considered fair, because I can forbid my antagonist to overtake just by moving my car, forbidding the overtake, but using an unfair strategy. So can you formally distinguish between?
Yes. So a very good question, because both Formula One and IndyCar are quite stylized in the sense that they have very, very strict rules. You are allowed to block something, and it is true that you could try to spend your entire time blocking, but that Markov game can defeat the strategy that if somebody just tries to block, you can do an appropriate slowdown and then slingshot past this. Another strategy that people use is to try to, and you've probably seen this when you watch races, Schumacher was reputed to have coasted behind someone until the last lap, used the slipstream of the person in front and then slingshot at the end. So all of those kinds of strategies, they get taken care of in this Markov potential. And amazingly, after you're done with this, when we show it to professional car drivers, we have two of them on our team, they can immediately understand how the mathematics corresponds to how they will drive. Having said that, I think human serendipity, I forget who the champion is nowadays, it's the other guy, Lukendahl, something like that, Formula One racer. It's I think that they still have a few tricks up their sleeves. And if you, and just a little bit like John Scott, these are tech. They have more strategy involved. When they wait, it's a 100-lap race, you wait to the 80th lap and 90th lap. We haven't got that all built in. But I think just like with other games, chess, Go, and so on and so forth, in January 2025, we have a wonderful woman race car driver who's going to come to Las Vegas, and we're going to go, and she's going to drive a Maserati, not racing Maserati. So we're going to race against her. Human against AI is in tech. And let's see how it will be. 10 laps, the Las Vegas Motor Speedway. So we'll see. We'll see. You know, they call it the go-to computers, go-to players or chess players. So we are hoping that January 2026 will be that moment. And of course, you know, the reasons you do this, the reason you do this racing, all the car companies do racing, because they harvest the techniques and they put it into their production cars. If you want certified autonomous cars, those technologies need to be matured on these cars.
Okay, thank you again.
Thank you.
If there are no questions, okay, thank you again for your interesting speech, and it's quite late, and so we. Okay. It's late for us for our coffee break, but maybe for you it's worse than for us. Okay.
Thank you very much, and I wish you all the best.
So. Okay. Thank you. I saw Marika making the gesture of late, but I was thinking about our coffee. Okay. Okay. Thank you to all, and let's have a half an hour. What is the? Okay. At 11:30 we'll be here again. Thank you.
Okay, good morning. Welcome to this session, sharing memories about Marika. And I'm very excited, moved, so I wrote down something since it's difficult for me to talk about this. So now I start this session and introducing the talk, which is in program entitled Hybrid System in Automotive Application, starting a successful academic-industrial collaboration by myself and Andrea Ballucchi. So the technical aspect of this talk will be presented by Andrea, and I will introduce the general problem and my personal memories about Marika. So first of all, I prefer to write Marika instead of Maria Domenica because she's the way. Now I need my glasses. I don't know where. Okay, done. So the first memories I have are related to the time when she was my teacher. Starting in 1991, she supervised my master thesis and then my PhD and my postdoc research. And this picture refers to the defense of my master thesis defense. And you can see Marika and Professor Isidori, so the best I could imagine to have. She was an example for me as a student and supported and motivated me for 5 years till 1996 during my PhD and postdoc position here in the University of L'Aquila. In particular, her enthusiasm for research inspired me and motivated me to begin my academic career. Moreover, I'm deeply grateful to Marika for giving me the opportunity to spend a long time at the University of California at Berkeley, since it was a very formative experience for me. From a research perspective, the collaboration with Marika spanned almost 20 years and mainly focused on the control of nonlinear systems and that of hybrid systems. In fact, my first paper at all, is with Marika and Jesse and dated 1994, both of you. while the last paper dates back to 2013, so 20 years. The collaboration with Marika was very fruitful as it produced 22 papers on conference and journals and so on. The first topic of research provided a design methodology for approximate output tracking for nonlinear, non-minimum phase systems. And this methodology was applied to different classical non-minimum phase systems such as R-plans and robotic arms with elasticity. The second topic of research provided a design methodology for the construction of dynamical observer for hybrid systems. The observer must detect both the continuous and the discrete state of the system, that is, the location in which the hybrid system is, and the value of the continuous time variables of the systems. The main idea is to use the result on observer for continuous time system and observer for discrete event systems. But if you have an hybrid system like here in the picture, you may have some input event and some continuous input, and you may have some output event and some continuous output. The problem is that in the general case, in the general application case, you have no discrete output that are generated when a transition takes place. So you don't know when a transition takes place. So the idea is to use a transition detector that mainly is a bank of Leuenberger observers that detects which of the dynamics of the hybrid system is applied, so detect the transition and provide this information to the discrete observer. Then, when the location is determined, one can use a classical continuous observer to observe the continuous time variables. This methodology was applied to the actual gear identification for a car, in which the input is the gear selected by the driver. You don't know the input. You have, when the driver selects a different gear, the dynamics of the system changes. And so you have to detect which gear is engaged by just having as a feedback the continuous time evolution of the continuous variables. So this methodology will be illustrated in a while by Andrea in his presentation. So as a student and researcher, I spent so much time with Marika that she became more than a colleague, I say a friend. So I totally agree with Jesse that fruitful research depends mainly on the joy and pleasure of working together. And Marika is very special, important to me, that for me it's very difficult to express all my feelings. So I try to select all the qualities I have come to appreciate over time. And I hope this is not too much over-sentimental, and this is disclose my presentation. Thank you so much. Now it's my pleasure to introduce Andrea Ballucchi, who is the founder and the CEO of Pure Power Control, and he will present the details about the methodology to construct dynamical observer for hybrid system and the application to industrial cases.
Thank you very much, Luca. Good morning, everybody. Thank you. Thank you. So, I met Monica the first time in 1997 when I joined the Parades lab in Rome. The mission of the lab was to support the automotive industry in the innovation of the design and development methods for the electronic control onboard the vehicles. So at that time, hybrid system was an emerging field of research in the control theory, and so with Marika and Luca was straightforward for us to apply the new emerging hybrid system techniques to the automotive sector. And in particular, we focus on engine control. So the first objective that is detectable modeling the internal combustion engine. In fact, at that time, the engineers in the industry developed an electronic control algorithm for the electronic control using mainly mean value module of the engine. But as you know, the internal combustion engine has a very complex behavior that involves both discrete components and continuous components. So we propose a model of the internal combustion engine where the phases of the four-stroke cycles are represented by the finite state machine. The first input, the spark, is an event, so in the discrete domain. The second input, the fuel injected, is again discrete in time but continuous in values, and the pressure of the intake manifold that is controlled by the throttle angle is instead represented by a continuous system. So this was a quite a novel approach to modeling the internal combustion engine, and was the basis for the development of several new algorithms for the engine control. The first one that we consider was the cutoff control. The cutoff control is a control strategy that is triggered by the engine control when the driver releases the gas pedal, so requesting no torque to be produced by the engine. But if this, in this case, to save the fuel and to reduce emission, the fuel can be shut off, but if this does immediately, then the elasticity of the driveline cause unpleasant oscillations of the driveline and of the vehicle. So before shutting off the fuel, the elastic energy of the driveline should be driven to zero. And as you can see on the picture on the right, the green trajectory is from experimental data when the fuel is cut off immediately. The blue line instead is the optimal control that we develop using the hybrid model of the engine to optimally drive the state to zero. And this is was our first control problem that we tackled. I'd like to mention a second one. This is the identification of the engaged gear that was already mentioned by Luca. This was the problem in this case, that the engine has to know in real time which if the gear is engaged and which gear is engaged. We first developed the methodology, a general methodology for hybrid observer design that was presented at the Hybrid System Computation Control Conference 2002, and then we applied this result to this methodology to the problem at hand. These are some experimental results where it is shown that the hybrid observer can, in a robust way and promptly, identify the state of the engaged gear with very little delay. So this is and we have tackled many control problems successfully, developing the application of the hybrid system control theory to the automotive and in particular engine control, but I will don't have the time to mention all of them. Later, the collaboration with Marika proceeds when I founded Pure Power Control in 2008, and there the mission of the company was to support the automotive industry in the design and development of electric and hybrid electric vehicles. So the focus of our collaboration moved from the engine to the powertrain, the electric powertrain. And we receive many students from America. And this is our current reference to our current research, common research, is related to the development of a model of a fuel cell vehicle, where in particular we focus on the hybrid modeling of the thermal management systems. I'd like to thank then the Marika for the profitable collaboration that we have since 1997. It was a real pleasure for me working with Marika. The scientific communities knows Marika for her important results in the theoretic in control theory, but I could appreciate also her passion in the control application and her deep attention on detail or understanding the problem and investigating how the most advanced control techniques can be applied to the real problem. I'd also like to thank Marika and in general the professors of the Department of Automatic Control of l'Aquila, because in my personal career, I always kept a tight link with the department and with Marika, and we receive many students, very brilliant students with a strong background, and for our work in the automotive sector, the knowledge of the system techniques is very important, and when they come to in the company, they are enthusiastic of applying the control theory to our problems, to our development, and this is because they receive very good guides in the university. So they are very enthusiastic, and this is granted to you and your colleagues. Thank you very much.
Now we come back to sharing memories. So it's my pleasure to introduce Professor Enzo Chiricozzi from the University of L'Aquila.
Good morning. Many thanks to Elena for the invitation to this important event, which focuses on the interesting and appreciated research work of my colleague Marika, pride of our Faculty of Engineering. In order to better frame the importance of the Center of Excellence in the development of the faculty, allow me a brief introduction. During 9 years of my presidency, I was convinced that the scientific role of the Faculty of Engineering was fundamental strategic importance, and I therefore devoted the constant efforts to enhancing and increasing the cultural heritage of the faculty, taking into account the wealth of high-level skills and the competencies present in the 5 departments of reference. This made it possible to expand relations with other national and international research institutions, to enter the main European research circuits, to increase contract and collaboration with industry, and to relaunch the internationalization process. I still feel the duty to state that the development and the growth of the faculty was possible thanks to the broad cooperation and the participation of all the faculty's components. And I underline that an important contribution was made by our colleague Marika. In fact, in March 2001, the Faculty of Engineering unanimously approved the institution of the Research Center of Excellence, DUS, dedicated to the design of embedded controllers and wireless systems. Our colleague, Professoressa Maria Domenica Di Benedetto, was appointed director of the center. The center's previously planned research activities were immediately launched, and the excellent results achieved were the subject of important papers, which were then published in prestigious international journals. And it is my duty, even today, to thank Marika and all the researchers in the DUS Center of Excellence for having contributed to increasing and spreading internationally the scientific credibility of our beloved Faculty of Engineering. Many thanks to you, Marika.
It's my pleasure now to introduce Professor Patrizio Colaneri from the Politecnico di Milano.
Okay, thank you very much. Thank you, Elena, for inviting me. I was waiting whether or not to give this talk because I remember a phrase of Mark Twain, the writer, saying that in order to, it takes a lot of time to prepare a 5-minute talk. I mean, which is improvised, by the way, 5 minutes off the cuff talk. So, I mean, but then I decided to recollect some memories and say something about that. Unfortunately, I was not your student because we have more or less the same age, right? But I remember the first time I saw Marika in probably during one conference in the early 80s, by the way, in Como, in our national gatherings and so on and so forth. I don't remember what your presentation, of course, but I remember that was completely struck with by your beauty and elegance, impeccable style, and so on and so forth. So I mean, and I'm present now that you still all this beauty and charm is still there. And you agree with me, Jesse? You didn't understand, okay. So the second thing is that nobody said yesterday, but maybe you have noticed that Marika is a woman. You noticed that? Okay. So, and to be, at the time she was, her fame was already on the rise in the early 80s, probably in the late 70s, but it was very difficult for a woman to be in an environment of men. We never talked about that, but probably you have some obstacles, let's say, or some difficulties in doing that. And this makes more, in some sense, commendable your incredible career later on. So that's also a second thing that I want to say. The third, that is the best merit of Marika, I mean, was back in 1999. Maybe you don't remember this, but you were in the commission that promoted me as full professor. And so, and this, probably you voted against, I don't know, but but I mean, and that's my recognition for you. I mean, they grew exponentially after that. I mean, so, and as colleagues later on, we had many occasions to meet in conferences, a lot of talks about our family and so on, and also in commissions of professorship, where I appreciate your also your care with not only with for the numbers of the publications and so on, but also with the problems of people, human, let's say, sensitivity. I don't know how to say. Okay, so this is another thing. The other thing is that you know that I mean, our job is. It's not really a job. I mean, I don't remember who said that being a professor is better than to work. And that also Giorgio Parisi, a Nobel Prize, said that. Also Enno Flaiano, which is a Abruzzese journalist, was. Now I remember. And so actually our job is something really strange. I don't like these, you know, these professors that are hieratic, sitting on the throne with slaves, by the way, PhD students sitting around. And so Marika is not this kind of professor, of course. So, you know, Marika, I like to be a little bit ironic on that. I mean, you know, Marika, the jokes of the three parrots. You don't know the joke of the three parrots? So there was a man that wanted to buy a parrot, okay? He went to a bird shop and he saw 3 cages with 1 parrot in each cage and asked to the owner of the shop, okay, how much it costs this parrot? Okay, oh, this is 1,000 euros. Oh my God, what is he doing? Oh, he can say goodbye, good evening in Italian, good night. Okay, and the second is 5,000 euros. Oh my God. Oh, because he also sings some songs. He also speaks German, English, and so on. He calls you in the wake-up call. And the third one, The first one is 50,000 years. Oh my God. I was astonished, but he said, why? It's so high price. Oh, because he can do anything, nothing. But the other two call him professor. So that's our job, right? And okay, just to end this, I mean, Jesse, you can bring back home this and translate in a very beautiful and less plain English, right? To give your colleagues, if they are ironic enough to understand this. And the last, I mean, when you have, I mean, so what you did here in L'Aquila, you and Alfredo, of course, is extraordinary. You're full of culture and experience. You know that experience feeds culture, and culture is embodied in experience. So, and when these two things find an happy intervening, so some secular miracles occur, right? And this in L'Aquila was a sort of secular miracle. And so I appreciate, of course, all you did here. I try to, let's say, give back a little bit when you asked me to be a commission in Aquila and whatever for PhD students and so on. I accepted with glad. And what I can say, that retirement is a sort of a watershed, right, between what is before and after, right? And so this makes me think about something that, since I'm going to retire next year, by the way, so I think, so what we leave to our students, to our younger colleagues, and so on and so forth. And so there is a sort of definition that I don't remember where it comes from, that the meaning of a real gift. A real gift is something that is a gift that who receive it doesn't need it anymore. In the sense that probably comes from, let's say, some Christian heritage because of the water, the lady in the well, the water, and saying that if you drink this water, you still are thirsty, but if you drink my water, you never thirsty. So I think that this, your quality is this, that you have left something that is completely embodied in the people that follow you. First of all, in Elena, in Pier Domenico, in Costanzo, in Stefano, in Giordano, and all the other people, in Vittorio, the younger one. That, and so, thanks for your leadership, and don't forget next year to come in Korea to play the piano in the IFAC orchestra with me. Thank you.
It's my pleasure now to introduce Professor Claude Moog from the University of Nantes.
Thank you. Sorry, this is a kind of last-minute contribution to this session, so it's not that well documented, but I can share some memories about a decade, a little bit before your students, because it was I got to know Marika when I guess both of us were completing or running or getting our doctorat d'état degree, which is a French degree which no more exists, but we got it. You, Marika from Paris, and myself from Nantes. So this was our period when I got to know Marika and all of my colleagues in Rome. Okay, I have to give a little bit my personal story. It's 1986. I guess that I had the opportunity to come for 6 months to to Rome under the supervision of Alberto Isidori. There are many people in this room who were directly or benefited of the supervision of Alberto Isidori. So I shared a big office close to San Pietro in Vincoli at that time. Of course, with Marica, Salvatore, Dorothée, who was passing by, and also Jesse for 1 or 2 weeks. So I will not repeat what I said yesterday, but okay. I just adapted a little bit my slides. So we had the opportunity to share some ideas and to work together. And okay, our feeling was that it was quite successful from a scientific point of view. I have to explain, I had only one, because I'm not that well organized with my personal photographs, not that much. I discovered much more information in Jesse's pictures yesterday. But one interest, so it's taken from this picture, which was taken in Phoenix, I guess. There was a conference in 1987. Marica's contribution was also at that time. She took me to some Torino conference at the end of my stay in Rome. Okay, there was a kind of meeting. And so thanks to Marica, of course, I could be introduced to other groups of researchers in Italy. And so this picture gives me the opportunity to mention some people who were at that time working at the University of Genova. After that, they moved to Ancona. Especially, at least yesterday, maybe today, there are some students working with Conte Perdon who were in this room. Maybe they are still here. Okay, at that time, we had no children, I would say no worries, perhaps. And okay, Marica apparently was drinking lots of beer, but and after that, we shared our experience. So maybe it was not okay. I have not a very good memory, so the dates are not very good. It was rather earliest in '89, maybe 1990, that Marica went to Nantes with her because we wanted to invite her, and she accepted to come to Nantes. And we were very glad because we got not only Marica, but not 2 generations of the Di Benedetto family, but 3 generations of the Di Benedetto family. And so so it was the beginning of a social life, a very active social life, even before their arrival, because today I have to acknowledge the work of my colleague, Alain Glumineau, that we saw shortened some picture yesterday because he was very active. He had more experience about French kindergarten and that we name École Maternelle. And I saw Maria somewhere here, so I can share, but she's perhaps with Livia. I can also share some, Marco is here, but I can share some memories with Maria, just mentioning that Alain Glumineau was very active in finding a suitable école maternelle in the neighborhood, and maybe she changed even. She tried several kindergarten in Nantes, so yes, and so she started with academic French language, not at École Française de Rome, but probably at École Maternelle La Bourgeonnière in Nantes. And this thanks to some of my colleagues who were, once again, more experienced. And, we had the opportunity, I think some picture by Jesse showed some I don't know where we were living, in the small apartment or already in our house in Nantes, but we had the opportunity to share some moments with you, your parents, and Maria, I guess. Unfortunately, the three generations had to live in some small university apartment. But I felt that even for your parents, it was, they were coming back to some younger years. They felt much younger than their physical age at that time. It was my impression. And it was a good opportunity to tighten intergenerational family ties. Of course, it was just for a few months, but it was my feeling at that time. Okay, after that, we had some short. Yes, it must be 1990 that we had this reciprocal experience. So we were going on working. Alain Glumino is a co-author of all this, so he was also involved in more pragmatic aspects of our experience. Okay, this is. I'm sorry. I'm pretty sure that I had some pictures from our apartment or house, but it's my today's contribution for this fantastic adventure for at least 1 decade of our respective lives. Okay, there's Bostwick Wyman from Columbus at Ohio State University. Some people, the picture is not the high quality, but okay. From that time, I got a little bit involved with other people, and okay, as I said yesterday, I worked with Conte Perdon for a few years, and everything like that is due, of course, to Marika. Thank you so much.
Now it's my pleasure to present Gilberto Burgio from Collins Aerospace.
So, thanks a lot. It's a pleasure and an honor to have been here these 2 days. And I'm the voice of the industry, like Andrea before, right? And I can say that it was a great story, right? Started quite some time ago. So Marika was my thesis supervisor in 1991. So since the beginning, right, of the same time of Luca Benvenuti and Stefano Di Gennaro, more or less, maybe he a bit earlier. And since then, actually, Marika and Professor Isidori, indeed, they inflated in me the passion in controls, right? So, and it's still there, right? So after 34 years, and it's nice that, so my career then went to the industry, and we had collaboration, of course, with the industry, because I was lucky to be in big realities who could afford as well to push research and advanced engineering. And and then many collaborations, actually, they were already mentioned before as well. You, Marika, you mentioned Magneti Marelli, and as well Luca and Andrea Ballucchi were mentioning collaboration on engine control. I mean, it's a great challenge, right? So it's not only controlled, it's as well real advanced technology development there, right? So, and I was lucky to be there. Then after, I was lucky again because I changed to Ford Motor Company, another reality where it's done a great job in pushing the technology, and there too with you, Marika, and then with Stefano, and some researchers then came up doing again interesting work in vehicle dynamics, right? So it's fun, right? It's not only passion, technology is as well fun, right? So, and there, Alessandro Borri, right? Domenico Bianchi, Temo Acosta-Lua from, I think he was a postdoc from University in Mexico, in Guadalajara, likely. And we supported some research with him. And it's still we are still in contact, so just recently we got some exchange of messages. And then, so this is automotive, then airplanes, right? So now I am in the airplane technology. It's a lot of things to do there. And we have been seeing these 2 days a lot of challenges to face in controls and in the direction that control is now taking. And it's evolving controls too, thanks to the big data story, to the machine learning. And it's just an open field to investigate and to deeper understand. So in aerospace, we have not done, so we should do something, right? So, all this nice story in my life, indeed, is as well paved with great human relations. So I mean, and that's important, right? It's not only a fact of being good in technology, in teaching, and is as well the human relation, right? The empathy, all things that you can teach, right, to everybody. So you are a good person, a great person. Was lucky for me to be in this story. So thanks a lot.
Now we have several speeches from ex-PhD students of Marika, but I want to remember that I was the first PhD student of Marika. And the first PhD student is like love, is never forgotten, okay? Let me introduce, and it's a pleasure to introduce Alessandro Borri, which is from CNR.
Thanks, Luca. Good morning, everyone. It's an honor to be here. It's also difficult to talk after many esteemed and appreciated colleagues. So in this slide you can see the one picture from the College of Engineering in Roio, in the mountains surrounding l'Aquila. That is where I collected most of my mind memories for my bachelor and master studies. As you know, after the earthquake, our field of engineering came closer to the center of l'Aquila. So the trigger for this presentation was that like at midnight a couple of days ago, I was able to find a picture of my master degree. And for the first time after many years, I turned it digital so that now I have also for my records. And so I met Marika as a student in my early years of bachelor in engineering, so more than 20 years ago. And she, together with Professor Germani, Pier Domenico, and Costanzo, and most people that are also here, Stefano, Giordano, were able to inject the passion for this field. And so after some years, and at the end of the master's path, I accepted to go for a internship at the Ford in Aachen, after the guidance with the guidance of Gilberto, who I had also the pleasure to meet here after many years. So I'm very happy for that. So after this start in the automotive field, I pursued a PhD in computer and information engineering. Okay, I don't have a picture for the doctoral dissertation, but so I used the previous one just from another angle. But as you notice, Marika looks exactly the same as some years ago. I don't, but I like to think that I look better now, but just an opinion. Okay, so during my PhD, I turned towards hybrid control and cyber physical system, and I was co-advised by Giordano Pola. So collect just a few snapshots. So we fast forward to like 10 years after my master thesis. So after a 1 year postdoc with Marika in l'Aquila, I moved to CNR in Rome, and we were able, mostly Giordano, Marika, and Pier Domenico were able to collect much work of those fruitful years regarding formal methods for the control of large-scale and networked system, which led to this honor to share the stage in the Scuola Sidra 2017, which is the Italian PhD school in automatic control in Bertinoro. Now we go rapidly to the modern times. And so what I believe to be a recent success story is the fact that I was able to co-advise with Marika some very good PhD students, Ilaria Di Loreto, and more recently Chiara Romano, that you listened yesterday in the morning session. She works on modeling and control on biological application, in particular tumor growth, and she was able to get a Best Student Paper Prize at her very first international publication. So we were very proud of that, and so we got this photo in the last CDC, but yesterday we were able to replace the fake Marika with the real one after dinner. So what happened along this journey? I consider I have the privilege of share with this history of mentorship at the beginning, and then collaboration more recently, including, of course, the 2 theses, 1 year postdoc, some research periods abroad, from Aachen, UC Berkeley, Santa Barbara, and Stockholm, when I was honored to visit Kalle Johansson. And more recently, when I got the permanent position in CNR, I was able to open also a small office of our CNR IASI in l'Aquila, and we were able to sign a scientific agreement between DUSE, the Central Excellent DUSE, and the National Research Council of Italy. We, of course, share teaching and master's project, the 2 PhD students that I co-advised, and more than the publication, and also, last but not least, many fun moments. And a privilege that I think I have, probably with respect to the previous speaker, is that I think that this history has still not come to an end, because only 1 week ago we were in Rome talking about science, of course, eating, because this is one of things that we like to share moments together, and also probably no more than 3 or 4 days ago, my last technical email to Marika and her reply. So this is a journey that I hope will be never ending. And so as I was saying, we shared fun moments, including, as you might guess from the last 2 days, many moments in which we like to spend time together and eat together, as from also the pictures that you see surrounding us during the coffee break, and also fun moments. For that, I mean, this was Marika's plaster is real. My is fake. I thank Costanzo for the Photoshop, for the editing, and I thank you very much for listening to this, and I thank you, Marika, for your support, guidance, and mentorship over the years. Thank you.
Now it's my pleasure to introduce another ex-PhD student of Marika. Is Giovanni Girasole, now is embedded system manager in Renova. Thank you.
So finally, first of all, I would like to thank all the people who make this happen, because it's I'm very happy to be here. A lot of people, I haven't seen them for a very long time, and it's very important for me to meet face-to-face Marika, Elena, and also my friend Giordano, who is in the... what I can say is that Marika has been very important for me, for my career, because when I started, when I was searching for a tutor for my thesis, I was looking for somebody who can drive me not only in the academic world, but also in the industry world. So it has been very important for me to work on my thesis in the research center Parades in Rome, where I have the privilege to meet Luca Benvenuti and also Andrea Ballucchi, of course. And following this experience, I was quite lucky because I have immediately the opportunity to join Magneti Marelli as a consultant. So starting from then, I come back here at the university to to get my PhD degree, and after that I was I joined again another industry, always in the automotive field. So I think that the most important lesson that I received from Marika is the way in which she treated all the people. I mean, she was always very, very kind, very, very warm with us as students, and also as, engineer during our life. So the first reaction when Elena and Giordano told me, there is this event because Marika retired, I was a little bit surprised. Why she retired? She's so young. So I was wondering why, but to be honest, at the end of this year, I'm turning 50, so even I'm not so young. So it's something that, okay. So I would like to thank you, Marika, very much for driving me during my life, and I think that the man that I am today is also thanks to your driving. Thanks a lot, Marika.
It's my pleasure now to introduce another ex-PhD student of Marika, is Gabriella Fiore, now in ABB.
Okay, so I'm very happy to have the chance to thank Marika. Because basically she has been my supervisor starting from my bachelor up to my PhD together with Elena. So I had the chance to spend several time with her, and she introduced me to new opportunities, like for example when I had the chance to spend my master thesis internship in ABB Corporate Research in Sweden. And when I then had the opportunity to be at UC Berkeley during my PhD, so this helped me broadening my horizons. So it has been very, very good for me. And basically, this means that you help me grow not only professionally, but also personally. So in a very short way, I really would like it's a wish from my side for my daughter to have the chance one day to meet a mentor like you. And thank you, Marika.
Now another ex-PhD student of Marika, he is Alessio Iovine. He is now in Supelec.
So thanks for the opportunity to be here. It's really a pleasure and an honor. I met Marika as a student during my last final year in automation and control engineering, and I remember I was really with the wow effect when she was teaching a hybrid system. I really felt in love with the argument and the way Marika teaches, and that was maybe the first spark when I started that I wanted to work on this field and really to do research. While I learned, I didn't really have idea what research was. Then during my PhD with Marika and Ellen, I think I started understanding a bit about it. And during the years, I always kept the connection, but I would like just to maybe name one or two things. We said that Marika is kind. I admit I've never seen someone from someone else. I've never seen the kind of emails that Marika managed to write. Even in the worst context, she's always gentle, always capable to find the perfect words to say what she wants to say, but in a polite way. This is really something that makes me wonder how, if you can exchange email with Alberto, which is really not at the same, let's say, attitude, really direct. So I really wonder how it works. And I think I try to learn also these characteristics, to say that when I try to learn, it's not only with respect to science, but Marika also taught me and the other PhD students, I think everybody else, a lot of other soft skills that are part of ourselves nowadays. I really hope so. Another memory that got in my mind, it was, well, once we prepared the control exams, and maybe it was a bit tough, so we were complaining when we were correcting them that the students were not good enough or something. And then Marika, just speaking like not a matter, she said, hey, you know, when I also had to help my son with the admission to Polytechnic, he asked me something on control, and I admit I didn't really remember how it was, etc. I don't know if it's true. I would like to ask Marco if this is a real reality or just Marika way of telling us that maybe we needed to be a bit more kind on this matter. So this is just to give a glimpse of what I hope to have learned and keep learning from Marika. And so to me, she's really a role model. And I wanted to make a joke, but thanks Alessandro for stealing the photo, because in the picture with Marika with a Band-Aid and the fake one of Alessandro, there is also one with me close by. And so the joke would have been that Marika is such a role model that even when she has a Band-Aid, we want to look the same. But yeah, so sorry for that. So thanks, Marika, and well, I hope to keep working with you.
We have now two more ex-PhD students of Marika. The first is Marco Mirabilio, which is now in Huawei, and he sent a message that I'm going to read. So it's in Italian, the message. Quando ripenso agli anni da studente dottorando all'Università dell'Aquila, mi vengono in mente tutte le persone che hanno contribuito alla mia crescita ed è sempre difficile trovare le parole giuste per esprimermi. Di Marika mi hanno colpito il suo interesse e impegno costante per la ricerca, cose che ho avuto il piacere di apprezzare maggiormente standole accanto durante gli anni del dottorato, anni che mi hanno permesso di scoprire anche la persona oltre l'insegnante. Posso affermare quindi la mia ammirazione per lei, sia come professionista che come persona. Tutt'oggi rimane un esempio da seguire e che mi ispira a dare il meglio di me, sperando di raggiungere anche una minima parte dei suoi successi. Sperando che non sia fuori tema, approfitto di questo messaggio per mandare i miei saluti a tutti coloro che mi hanno aiutato in quegli anni, come Alessio, Elena e Giordano. Infine, rinnovo i miei ringraziamenti e congratulazioni a Marika per la sua eccezionale carriera. Now it's my pleasure to introduce Domenico Bianchi, another ex-PhD student of Marika. We should have a video.
Yes, do you hear me?
Yes.
Okay.
Yes.
Good morning, everyone. First of all, I would like to thank you for organizing this event together with collaborators. I'm deciding event. I'm sorry I can't be there. I began because of quantum computer engineering l'Aquila in the use of the second. The first or second year of this degree course, following a national reform. I enrolled with curiosity for computer science course, but in the third year I decided to opt for the automatic path, a path with more mathematical roots, and I began partially thanks to Marika and the Domenica teachers, almost all of whom are there today. I would bring my memory of Monica under different aspects, professional but also human. The latter only remembered and shared by many of you opposite. In terms of time, I decided to do my thesis with her, and I had the opportunity with the Ford Research Center in Aachen, with co-supervisor Gilberto Giorgio. Fantastic experience under many profiles that made me grow and allowed me to delve into the application level of integrated control of lateral dynamics algorithms. Then I started working for Ericsson in Milan, and with my job to start my PhD in Malta. I want to underline this because like all those who enter the world of research, I earned my salary for passion. It was 2008. I started full of enthusiasm. Then there was an event that affected the city of L'Aquila, the week of 2009. Everyone was disoriented, a city on the ground, a disaster event. Marica managed to transform this catastrophe into an opportunity by staying close to us, PhD students. The time to get visa and I went to the Center for Automotive Research in Ohio, and I started delving into the world of hybrid electric vehicles, following George Vitsonian's memory. Like me, other colleagues, some in Santa Barbara, Salvatore, some at ETH, for example. An experience that reached me from technical and human point of view. Then I continued to do research always with the character of networking and international and national collaboration. Thanks to Marco with Antonella Ferrara, then Renault on highway traffic control. I have therefore worked in the automotive application sector in its broadest sense. This was also very useful to me when I worked in 2016 for Fiat Chrysler on Illinois. I just want to mention that training was fundamental, also thanks to the national recognition of doctoral schools that Marica wanted me to attend. So, with this little memory, I want to tell how professionalism, humanity, and working forecast the strength of internationalization. With this now engulfed research after years have been characteristic and pillars with which I would always remember Mario. Good continuation to everyone. Thank you.
So the list of ex-PhD students of Marica is finished. So now it's my great pleasure to introduce Maria Gabriella from the University of Rome, and most importantly, Marica Sisters.
So thank you, Luca, and thank you, Elena, for having me here. So I would like to first introduce myself. I am the little sister. So by definition and in practice, that has meant watching, learning, and trying to imitate my big sister Marica, whom I have always called by a special name, and this name is Yaya. For a baby, it's difficult to pronounce Marika. But this name stayed. You know, I really wanted to do everything she did, everything. And from the earliest time steps, I tried to track her trajectory, to imitate her control strategies, and to stabilize my own growth using her as my reference model. Yes, yes, Yaya has been my model since the very beginning. I can say I have met her on March 16, 1958. But what a model she has been. Her accomplishments are uniquely hers, elegant in execution, rigorous in thought, and deeply influential. In preparing for this event, celebrating her excellence, I attempted something bold. I opened one of her reference classic papers. The matching of nonlinear models via dynamic state feedback. To my surprise, it was incredibly illuminating. And so I'd like to share with you my personal interpretation. Yes, this is us. I think there is a pointer here. How do you use this? I mean, the one on the right, it's Marika. Yes, this is Marika. And the one on the left is the little sister. So would you agree with me that matching this model is simply impossible? And if you're not convinced, let me draw your attention to one detail. Look at those legs. Look at that. You know, it's mission impossible, right? So, though I may never exactly replicate her trajectory, hers being uniquely complex and gracefully nonlinear, I take pride in tracing her orbit, because in doing so, I have found my own direction. Her path has not only guided me, but shaped the very coordinates of who I have become. And her journey, as I could see today, and actually I already knew that, doesn't just illuminate my way, it radiates outward, lighting the path for so many others. It becomes more than a personal achievement. It becomes a beacon showing what's possible. But I know that from my early days and my first lecture in systems theory back in 1979, that in systems theory, initial condition matters. And so do the forces that guide you there. For us, for Marika and I, those forces were our parents. Still at the beach, and they were the designers and the steady state reference we keep returning to. Together, they built the foundation from which both Marika's flight and my orbit could begin. So yes, I may still be the little sister in many ways, but I've come to realize that the best systems are those that learn from the very best inputs. And lucky me, mine came from Yaya. In the language of systems, this is a story of feedback, influence, and convergence. but in the language of sisters. It is simply love, admiration, and deep gratitude. Do you notice what I notice? I mean, do you see the posture and what she's doing with her arms and her hands? She still does that thing. So thank you, thank you, thank you for being my model, my mentor, and my forever inspiration. I celebrate you, not only as a brilliant scholar, but as my reference model, my lifelong feedback loop, and the best big sister anyone could ask for. Thank you.
It's now the time of Maria Ricci and Marco San Giovanni, the daughter and the son of Marica.
This is a tough act to follow, but we'll manage.
Indeed, last but not least, the children. Today we celebrate not just a retirement, but the transition. Because let's face it, when someone's specialty is nonlinear systems, you cannot expect a path straight as a line to slowing down.
For our mom, it seems that, the retirement is just a new kind of multitasking. She's someone who's never still, if you've met her in a family situation, unless she's asleep. And that doesn't happen very often, nor easily. And I've witnessed this past days as we're sharing the hotel room.
Mom, to sleep better at night, you may want to try, just maybe, to perform breathing yoga exercises a tad less, and maybe try to think about this stellar career, full of achievements despite all the resistance. Mom, these past 2 days, we all witnessed the hell of a career system that you completed.
So, and indeed, my mom believes so much in control theory that she may have applied it to a very highly nonlinear and complicated system. It's us. So, in that regard, let me just say that our house was definitely not uncontrolled.
Yes, feedback loops were very real. You gave feedback, a lot of feedback, a lot. Usually in the forms of detailed WhatsApp messages or lovingly intense interrogations.
To this day, there's an observer on my state that's still wondering whether I've had enough to eat. And this while I'm 6,000 miles away.
But we'd like to think that sometimes we also supported you. I still remember phone calls from Roma to L'Aquila and back, where I'd hear everything from university drama to what the reviewers did not understand about your paper, and also you asking in passing whether I'd left the dishwasher open again.
And during the IFAT conference in Yokohama, I'm quite proud to say that that presentation was rehearsed with me many times. And that I may apply soon for a PhD in control theory history.
Yeah, we grew up surrounded by research papers, grant proposals, and also a lot of love. And okay, maybe a few misread censors when we said we were studying and actually weren't, especially me. But Mom always tried to see the best in us, even if the lie detector was occasionally underdamped.
Who says life should follow a straight line? Not our mom. Whether it was nonlinear dynamics in her lectures or our chaotic schedules with schools, sports, and others, she handled it all with grace. And exactly the right amount of control, at least according to her.
Hybrid systems, she mastered those, whether it was juggling, Roma-L'Aquila commutes, deadlines, my kids' pickups and schools, schedules. Mom did it all, sometimes with a Bluetooth headset and a pot of pasta going at the same time, unfortunately going a little bit too often over time.
And let's not forget, we saw many pictures of this, that she brought her billions to conference all over the world. IFAC in Mexico, CDC at the Bahamas, and elsewhere. Very selflessly, we children, we always made the effort to join her. And of course for the science.
She published, taught, mentored, and built a community of colleagues and students who are more like extended family. And Elena and Jordana, to name a few, you are practically part of our WhatsApp family group.
So thank you for all the support you've given to my mom these years. We know it.
Now, Mom's entering a new phase. One where control system classes may be swapped for music sheets, where jazz may replace journal articles.
And don't be surprised if she composes a piece called Hybrid Stability Blues as well.
She's planning travels, Vietnam is on the list, exploring her passions and practicing yoga, a lot of yoga. We're half expecting her to start teaching that as well.
Because if there is one thing we know, Mom doesn't do anything halfway. Retirement is just another system to master with elegance, precision, and maybe some new yoga pants.
Oops. Mom, your career wasn't just about systems and equations. It was about people. You powered generations of students, colleagues, and us.
You showed us passion and perseverance can coexist with unconditional love. How a woman can thrive in a male-dominated field, as Patrizia was saying before. And she could raise a family and be there fully for her 2 children, for both of us.
And beyond.
And beyond now, yeah.
You were always active, always present, sometimes too present. We still get 8 questions, WhatsApp messages about every single thing. But we wouldn't trade that for anything.
So maybe let's try, Mom, to keep the WhatsApp messages to 3 questions. So thank you, Professor Mom, for all the feedback, the love, the laughter, and the lessons, both in control theory and in life.
The best circuits really are the ones that power others. And you, Mom, are the best powerful of them all. Thank you.
This was the last speech, so thank you for attending. And Elena, do you want to say something?
I'm really touched, moved. So it's difficult now, but I want to thank you. This is really the most important thing I would like to say. I would really like to thank you for these days. They will stay really in my memory, my heart. And I have to thank, first of all, Elena, for organizing this wonderful workshop and all the effort you put into that. This has meant a lot to me, because it's true, it's a new, like Maria was saying, I think, right? It's a new period of my life, and this really means a lot. And Of course, I also thank all my colleagues and researchers and young people of the Automatica group who also helped for making this possible and to be here during these days. It has been a real gift, like Patrizio was saying, a real gift. So I would also like to thank the chairs of the sessions who are my colleagues in automatic control who have always been very close in all these years. So Giordano, Paula, where is Giordano? Oh, far away. Giordano has been my first PhD student in L'Aquila, so Luca, you still are the first. So, no problem. Stefano, with whom we shared a lot of traveling from Rome to L'Aquila and back and forth. We shared a lot of work in this traveling, and but also personal friendship. So, and also Costanzo, even if you are in a bad mood, you look at Costanzo, you listen to what his answers are to what you're saying, even if it is, problems or whatever, and you just laugh and you forget everything. So I must say, I have extraordinary colleagues. Without them, it would not have not been possible to have this path. And of course, not only my automatic control colleagues, but also all my colleagues, and some of them you could see today. Enzo was talking, I saw Marco Faccio, I saw many colleagues from the engineering group, from mathematics group, and I am really grateful to all of you. So this is really a real thank, like a real gift that I want to express. It is very difficult to express my feelings right now because I'm really a little bit moved, but I want to say this. I also would like to really thank very much the speakers for coming to L'Aquila, for all their words that are really so incredible to me, unforgettable, and for the outstanding contributions that they shared with all of us. I'm sure that especially the young people, but all of us could enjoy what you presented and said. And Alberto Isidori has been my mentor since 1975 with the automatic control course, and since then you were really my role model. Difficult to reach from a professional point of view. I don't have any slide, but this is for sure what I tried to do. So thank you, Alberto. And Jesse, Claude, Shankar, you have been my friends since many, many years. Colleagues, but real friends. And I really enjoyed to work with you. And the fact that you were talking about all this research we did in the 90s brought me back to the times where we were really happy for working and for enjoying many, many things together. So thank you very much, really. And Richard, John, Kalle, I met you when you were younger than me, so I met you when you were PhD students in Berkeley, and also a postdoc in Berkeley. I enjoyed your company, your enthusiasm in research. I really could imagine that you would be what you are now, stars in control, but not only, right, as persons and as professors. So thank you very much for coming here to this event. I really enjoyed it, to see you again and to listen to you. My former and present students, I really thank you, of course, for your words, and it means a lot to me to see you here. And you have been my motivation in my life and in professional life, and also my hope now that the future will be even better than it was for us. So from what I see, you can do it. And so thank you very much also for this. I thank also my colleagues, as I said, Enzo, who was talking before, Enzo, for your kind words, Patrizio, Claude, Gilberto. I don't want to mention everybody because I will, I cannot name everybody, but I really thank all the people who shared their memories with me. It has been wonderful, I think, also for everybody to know what happened during the years. I liked your snake, a very long snake. So I hope it will continue. And I was very lucky to have all of you in my professional life, and as you could see from what my sister was saying and from what Maria and Marco were telling you, our family life, I have been very lucky to have you all. So I cannot name all of you, but I really thank all the presenters for being here, for sharing with me these days and sharing this particular moment of life. And thank you, really, very, very much. It's okay. I was scared that I had to do like the Pope, stop it. Thank you. Thank you again.
Sorry. Can you come here for a photo together?